Linear functions. Well, they come in straight lines, okay, hence linear. But what are functions? Well, functions are special relations. Relations say that there's some relationship between two variables. When one variable does something, the other variable does a particular thing. Now, a function is a special relation where each member of the domain has exactly one member in the range. So in other words, if you specify an x coordinate, you have one and only one value for your y coordinate. This, for example, could be a function, this line. But this sideways parabola, yeah, well, it's not much of a parabola, but this one cannot be, because for some domains, well, okay, a lot of domain members, it has multiple ranges, values. So one independent variable value for one dependent variable value. So you put something in, you get a particular thing out. Not, oh, you could be here or here. So a vertical line test is you take a pencil or straight edge from left to right across a graph, and if it passes through only one point on the graph or no points, because, hey, it could be that the function only starts here and you're way over here, so you got no points there. So no more than one point on the graph, then it's a function. If it passes through more than one point, like here, then, like on this other one here, this other relation, then the graph does not represent a function. But wait a second. This is y equals f of x. So y is a function of x. This one, on the other hand, this could very well be x is a function of y. Like, if you decide to use y as your independent variable, it could well be that for every independent variable value, there's only one particular dependent variable. But the convention is you graph your independent variable on the horizontal axis and your dependent on the vertical axis. You can change the axis labels if you want. It could be a is equal to a function of b. But for our purposes, generally we go with x is the default independent variable and y is the default dependent variable. The dependent variable changes when you change the independent variable. So, the dependent is like your output on a computer, and your independent is like your input. And then the computer does the function in between. So it transforms the independent variable to give you the dependent variable. Now functions are relations, so they can be represented using ordered pairs, so points, tables, or graphs. Determine whether each relation here is a function and explain. Well, for every x value, for every first coordinate value, by default we say x. Like if we have a point that's represented using an ordered pair, or just an ordered pair, usually we default to that being a point and its x coordinate and y coordinate. For every x value, there's only one y value. So this could be a function. Be a function. of x. However, look at it. How many y values do we have? Oh, we have 4 separate y values, and each of them has its own unique x value. So, x could also be a function of y in this particular relation. But we won't actually write that down because we are not usually considering that at this grade level. Now 10, negative 10, 10, and 20. Well, for x equals 10, there are 2 y values. So, thus, not a function. A function. If you look at the y values for your 4 different points, you have 4 different y values. None of the y values corresponds to more than one x value. So it's not a function of x, but could have x be a function of y though. Of y. Yeah. Alright, exercises. Determine whether each relation is a function. Explain. Negative 5, 2, 3, negative 3, 1, 1, and 3, 2. Well, you have 2 instances of x equals 3 with different y values. So you have multiple y values for the same x value. Therefore, this is not a function of x. So x equals 3 has 2 y values. So y is not a function of x. Actually, yeah, let's just write that over here. 2, 7, negative 5, 12, negative 10, 2, negative 2, 12, and 1, 7. Well, we see that the x values do not repeat, so no x value has multiple y values. Thus, the result is could be a function of x. A function doesn't necessarily have to have a formula. The reason why I say it could be a function is, well, this relation, we don't know what happens, if anything, between these points. So, yeah, it's not disqualified from being a function of x. Of course, depending on your teacher, they might prefer it is a function of x. Or just it is a function, because it's the default is a function of x, f of x. Alright, here we have a bunch of different x values and some y values. Some of the y values are the same, but hey, all the x values are different. Therefore, x values don't have multiple y values. So, this is, could it be a function of x? Yeah, it could. But a lot of teachers would prefer it's a function of x. of x. Now here you have x equals 1 and x equals 1 corresponding to two different y values. Oh dear. X equals 1 has two y values. Therefore, so not a function of x. Representing functions can be done with equations. So for a linear function, if you have two variables, you usually go for y equals, you do something to x. However, x has to be to the power of 0 or 1. Now, why is 0? Well, y equals 5 is what? It's a flat line when you graph it. So, does x appear? No, so it's x to the 0th power. And x to the first power multiplied by some coefficient, that will also give you a straight line, with the coefficient dictating for every one increase in x, how much y changes. -2, that means for every one increase in x, y goes down by 2. Y equals 1/3 x, for every increase in x, y goes up by 1/3. Y equals x plus 1, well, for every one increase in x, y goes up by 1. Now, nonlinear equations, well, you can have degrees of x that are not 1 or 0. This, xy equals 4, that's just y equals 4 over x. Hey, do we see another of the same type here? Yeah. So, solutions of a linear equation are the ordered pairs that make the equation true. Of course, if you have a straight line of any length at all, even if it's just 1 unit long, you technically have an infinite number of ordered pairs because you can infinitely subdivide it. But for us, we're just going to find a few solutions, so a few ordered pairs that make the equation true. Why is this important? Well, let's say we want to actually graph this line. Oh, what are we going to do? Just randomly scribble on a graph? No, obviously not. So we're going to find a few points that are on this line, and then we're going to draw a line through those points. Example 1. Complete the table. Use the results to write 4 solutions of y equals 2x minus 1. Write the solutions as ordered pairs. Okay, y equals 2x minus 1. Well, x, let's start with 0. 2x minus 1 is 2 times 0 minus 1 equals -1. So y equals -1. X equals 1. 2x minus 1 is going to be 2 times 1 minus 1, so 1. Y is equal to 1. X is equal to 2. 2x minus 1 is going to be 2 times 2 minus 1, so 3. Y is equal to 3. X equals 3. That's going to be 2 times 3 minus 1 is 6 minus 1, so 5. And y is equal to 5. So what do we do with these ordered pairs? Well, we could graph them. Y equals 2x minus 1. Oh, hey, let's transfer this down here. X, y, 0, 1, 2, 3, -1, 1, 3, and 5. Okay, so the coordinates of all points on the line are solutions to the equation. Well, x equals 0, that would put us at y equals -1, so that's here. X equals 1, y equals 1, 2, 3, and then 3, 5. Oh, down here it would extend backward to -1, -3, and then over here-ish. Right, so you'd plot these ordered pairs and then you would draw a line through them. Please do try to use a ruler if your equipment permits you to use a ruler. And remember guys, pencil and paper do permit the use of rulers. Why do I say pencil and paper? Because lots of places they demand you use pen and paper. The thing is, when you're doing geometry or graphs or whatever figures, even if you have to use pen or paper for some reason, use pencil to do it first. You don't want to make a mistake somewhere and have to redo the whole thing. And believe me, mistakes happen. Like, perfection is not achievable. It is not a realistic goal. You can only approach it as much as you can, but if you don't plan for failures or errors, then you have failed to plan. Then you have erred in your planning. And also because pencil and paper, it's much easier to have different forcefulness to your lines, so different shades. I mean, there are some other reasons, but this is not a philosophical debate on the merits of pen versus pencil. All right. Exercises. Find 4 solutions of each equation. Write the solutions as ordered pairs. Well, y equals 2x plus 1. Well, that's easy. X, y, x equals 0, y equals 1. X equals 1, y equals 3. X equals 2, y equals 5. Y equals 3. So you list these out as 0, 1, 1, 3, 2, 5, and 3, 7. Y equals x plus 1. Well, you got 0, 1, 1, 2, 2, 3, 3, 4. 2x plus y equals 1. Well, that's y equals -2x plus 1. So we would find ourselves with, well, let's list out a table if we can't immediately just go, boom, it's this. So x equals 0, y equals 1, x equals 1, y equals -2 plus 1, so -1, and x equals 2, so 3, we have y equals -4 plus 1, -3, -6 plus 1 is -5, so that's 0, 1, 1, -1, 2, -3, and 3, -5. Okay, let's graph these equations by plotting ordered pairs. Y equals -3x. So, how can we do this? I'm going to go with this method. -3x, 2x plus 2, so everything in one big table. And y equals 3x plus 3, so rearrange as needed. 3x plus 3. And if we don't want to go way too far off base, we're probably going to be starting around say -3. Okay, -3. For -3x, that's going to be 9. So way out to lunch. -2, -1, 0, 1, 2, and 3. You actually don't need this many points. Like, you actually only need 2 points to draw a straight line. But considering we have a bit of a ruler issue with this equipment, more points doesn't hurt. So, -2 times -3 is 6, -1 times -3 is 3, and 0 times -3 is 0, -3, -6, and -9. 2x plus 2, well, 2 times -3 is -6, plus 2 gives us -4. -2 times 2 is -4, plus 2 is -2. -1 times 2 is -2, plus 2 is 0, and 2 times 0 plus 2 is, of course, 2. And for every 1 that x goes up, 2x plus 2, or y here, for this particular line, goes up by 2. So 4, 6, and 8. 3x plus 3. Well, -3 times 3 is -9, plus 3 is going to be -6. And then for every 1 that x goes up, 3x plus 3 is going to go up by 3. So -2 times 3 is -6, plus 3 is -3. -1 times 3 is -3, plus 3 is 0, and then you get 3, 6, 9, 12, and so on. Okay, so let's actually graph these. For the -3x, we show up at -2, 6 on this grid, and then we get to -1, 3, 0, 0, 1, -3. For 2x plus 2, we enter the plot at -3, -4, -2, -2, -1, 0, 0, 2, 1, 4, and 2, 6. 3x plus 3, well, we go from -3, -6 is off the charts. So -2, -3, -1, 0, and then 0, 3, that would be up here, and then 1, 6. And then we go off the charts. Now let's actually use a ruler tool for this. So the lines that could be graphed through the points we plotted look like this. As you can see, we have the slope 2. So for every one that x increases, y increases by 2. That's slope 2. And for every one that x decreases, slope decreases the y by 2. So that's slope 2, and it passes through the y-intercept 2. It passes the y-axis at the value of y equals 2. Where is the y-axis? The y-axis is found at x equals 0. Hence, that's this point. Now for 3x plus 3, we notice that it's steeper. The slope is 3, and it also has a y-intercept of 3. Now for -3x, that passes through the origin, 0, 0, because there is no y-intercept term being added or subtracted. It's just x equals a multiple of x. A rate of change is a rate that describes how one quantity changes in relation to another quantity, or how one variable changes in relation to the changes of another variable. So, example 1, find the rate of change for the linear function represented in the graph. Well, we see that for every 1 x increases, y appears to increase by 2. Same here. Same here. And also here, for that matter. For every 1 increase in x, y increases by 2. So y is equal to 2x. So for every 1 x increases, y increases by 2. And then, wait a second. If it was y equals 2x, it would pass through the origin. So we are going to move it to, minus 1, so that when x equals 0, y equals negative 1. Yeah, why North American math curricula often teach rates of change in functions without just saying, oh, this is a slope? Well, at least now you see where the slope thing developed from. So find the rate of change for the linear function represented in the table. You can see that for every 1 x increases, every 1 x increases by y increases by 3. Now the rate of change, considering we actually have units here, would be 3 degrees Celsius per hour. If you want to plot this thing with an equation, you gotta have y equals 3x, because hey, for every 1 x goes up, y goes up by 3. And then, do we need to make any adjustments? Oh no, it passes through the origin. Okay, so plus 0. The y-intercept is 0, so we don't write anything there. Let's find the rate of change for each of these linear functions. Time in hours and distance flown in kilometers. For every 2 hours, 100 kilometers per 2 hours, or 50 kilometers per hour is the rate of change. I think this is some sort of bird, because a manned aircraft that's flying that slowly, it's not that easy to lift a human, okay? So yeah, kind of weird. Now here we got y goes up by 60 in the space where x goes up by 4. So this change in y over change in x, the delta symbol is the symbol used for change. The change in y is 60 divided by the change in x, which is 4, is equal to 15. So the rate of change is for every 1 x increases, y increases by 15. And because it seems to pass through 0, 0, the equation is probably y equals 15x. I mean, unless there's a plus 0.01 or something just to troll us, but your teachers will generally not do that for this sort of question. The rate of change here, though, we go from 50 down to 20 when x goes up by 2. So x increased by 2 and y dropped. Do you guys see now why a lot of people just prefer this sort of notation? Or even just rise over run instead of verbally explaining? Because it's a lot less writing. So the change in y is negative 30 and the change in x is 2. That means the rate of change is negative 15. For every increase in x, y decreases by negative 15 times as much. So y is equal to negative 15x plus, the y-intercept is 50. All right, then. Relationships with straight line graphs are called linear relationships. They have constant rates of change. Now, a special type of linear relationship which has a constant rate of change is called a direct variation. It means that y directly scales off of x. It passes through the origin so that when x equals 0, y equals 0. And k, the ratio between them, k is called the constant of variation. I think you remember this from somewhere, like last chapter, for example, right? Okay, so example. As scuba divers descend below the surface of the ocean, the pressure they feel from water increases at a constant rate. This is shown in the table. These are in feet and pounds per square inch for some reason. Presumably because Americans like these units. Find the constant rate of change for this linear function and interpret its meaning. We know that it increases at a constant rate, and we know that at the surface of the ocean, where the depth is 0, the water pressure is also 0. Because there's no water pressing down on ya. Does this surprise anybody? I hope not. Okay, so 8.9. Okay, let's see if it actually holds true. When x doubles from 20 to 40, y doubles from 8.9 to 17.8. Wonderful! Okay. So the constant rate of change is let's use delta y over delta x. So change in y over change in x, which is going to be 8.9 over 20. Or you could say 17.8 minus 8.9 over 40 minus 20. And that's going to be 8.9 over 20. Divided by 10 is going to be 0.89, so 0.445. This is going to be change in what? Pounds per square inch per foot. Pounds per square inch per foot. You'll find that these units often do something very funny if you simplify them too much. Like if you divide by square inches and then you divide by feet, oh hey, those are going to end up being per 12 cubic inches. So the rate of change for this linear function, the units are going to end up being per 12 cubic inches. Or if you divide this part by 12, to get rid of the 12 in the denominator, you would end up with pounds per cubic inch. Yeah, fun stuff. Interpret its meaning. the rate at which water pressure increases with depth. Increases with depth. Well, I guess we're back here. Okay, one moment. What's 0.445 divided by 12 and then multiplied by, what was it, like 450-ish grams? That's like 16.68 grams, so about 17 grams. What about 2.54? That's centimeters per inch, so you cube that. Oh, hey, it's like 16.4-ish. What does that mean? You actually found the density of water. If you simplify the units, you end up with density of water, just in pounds per cubic inch. Density of water. But I'm pretty sure that's not what you're looking for in a math class. Like, this would be more like science class calculations on material density. Determine whether a proportional linear relationship exists between the two quantities shown in the table. Explain your reasoning. The ratio is constant. Or at the very least, it should be. Let's check just in case. Okay, 13.35 divided by 30 is 0.445, okay. 22.25 divided by 50, that's 2.225 divided by 5, or 0.445. Yeah, okay, the ratio is constant. So, thus, what? Thus, it's proportional. Because if you went by differences between the data points in the x-axis and versus the y-axis, you couldn't actually say this. But if you said that the ratio is constant between x and y, then yeah, you're fine. You can say that, oh, it's proportional because the ratio is constant. Write an equation that relates the depth and the amount of water pressure. So the depth is x and the water pressure is y. So y is equal to 0.445x. X is depth in feet, and y is pressure in PSI. PSI is pounds per square inch, and it's still a unit you see quite a bit, actually, even outside the US. Exercises. For exercises 1 to 2, refer to the graph below, which compares the number of chairs bought in an island resort and the amount of shoreline reserved for your beachfront property in meters. Oh, so that's why it says total coast. Okay. Find a constant rate of change for the linear function. Well, we see that from 0 shares to 4 shares. By the way, I'm very doubtful that you can actually buy partial shares, but some places do allow trading that. Interesting. If I recall correctly, the Globe Theater, as in William Shakespeare's place, they actually did do partial shares. At least they did in some novels I've read. But anyway, the rate of change is going to be the change in y over the change in x, which is 60 minus 0 over 4 minus 0, which is going to be equal to 15 meters. Yeah, coast, we should probably put meters per share. So the constant rate of change is, well, if we express it mathematically, it's going to be y equals 15x. Determine whether a proportional linear relationship exists. Straight line through zero, zero, thus proportional. Of course, it doesn't make any sense when you extend it past 0, 0 to the negative shares, because you can't really do that. But hey, write an equation that relates the number of shares and the shoreline length reserved. Well, y is equal to 15x. X is number of shares. Y is shoreline reserved. The slope describes the steepness of a line. The slope is equal to the rise, which is the change in y. Change in y divided by the change in x. So it is the change in y per one change in x. Over delta x. And it's between 2 points, which are x1, y1 and x2, y2. Now, x2 is not equal to x1. That's important, because otherwise you end up with divide by 0. If you end up finding that the slope between 2 points that you know are different, because their coordinates are not the exact same, if you find that, that tells you that although y has changed, x has not, which means that this is a vertical line and the equation is x equals some value. Whatever the x value those 2 points had is. So the difference in y and the difference in x, which point you label x1, y1 or x2, y2 doesn't actually matter. But you must make sure that the 2's come first before the 1's. You can actually do it just fine going the other way. It's just both the numerator and the denominator would become the additive inverse, so the negative of what they were supposed to be. And what happens if you divide two negatives? Or change the sign of both numerator and denominator? In other words, negative of what they were supposed to be. Well, the negatives cancel out, so it's fine. But you must make sure that your order is consistent. It must be y2 minus y1 over x2 minus x1, no matter which one you label x2, y2 or x1, y1. Because the actual numbers, you can swap them around. But the order they come in? No. So find the slope of the line. Well, m is equal to y2 minus y1 over x2 minus x1. For many reasons, people tend to use the point that has a bigger x value as x2, y2. Because dividing by negatives is annoying for a lot of people. So y2, that's going to be 7 minus y1, which is 4, over x2, which is 4, minus x1, which is 2. That's equal to 3 over 2. That is the slope of the line. Now let's do some exercises and find the slope of some lines. Oh dear. Okay, a flat line has a slope of 0. Because for any m equals rise over run, so 0 over not 0, which is equal to 0. Yeah, so a flat line which has a constant y value has a slope of 0. For this line, well, we can go with this point and this point. Yes, for this grade level, if it looks like it crosses the coordinate grid at an intersection of coordinate lines, so in other words, integer coordinates, it probably does for this grade level. This point is 4, 6, and this point is 2, 2. So, we're looking at m is equal to y2 minus y1 over x2 minus x1, which is equal to y2 minus y1 is 6 minus 2 over x2 minus x1, that's 4 minus 2. So that's going to be 4 over 2. In other words, 2. M equals 2. Now for this line, you go from 0, negative 2 to 8, 4. And the slope is y2 minus y1 over x2 minus x1. So y2 is 4 minus y1 is negative 2 over x2, which is 8, minus x1, which is 0. So that is 6 over 8, or 3/4. Now, what if we find the slope that passes through each pair of points? Well, m equals yb minus ya over xb minus xa, which is equal to 4 minus 2 over xb is negative 4 minus 2. So we end up with 2 over negative 6, or negative 1/3. Now for L and B here, the slope of LB is equal to YB minus YL over XB minus XL. To be fair though, labeling the slopes with subscripts is not necessarily essential when you're doing one slope per question or sub-question. But if you're doing multiple, yeah, you should definitely label all of them. So, YB is 2 minus YL, which is 5, over XB, which is 9, minus XL, which is 5. So that is negative 3 over 4. So that is M of LB. Yeah, we should also put that there. So now that we've made a bit more space, let's find M of RS. M of RS is equal to YS minus YR over XS minus XR. YS is 3 minus YR, which is negative 4, over XS, which is 7, minus XR, which is 7. Oh dear, we end up with 7 over 0. If you end up with 0 over 0, you should have checked the points before you started, or you did something very wrong somewhere. But if you end up with a number divided by 0, a number that's not 0 divided by 0, that's undefined. Which means these 2 points, they're on a vertical line. The line is x equals 7. The slope-intercept form of a line makes it easy to graph. For example, y equals mx plus b. The slope is m, and the y-intercept is b. Because when x equals 0, well, y equals b. And where is x equals 0? Oh, that's a y-axis. So b would be the value at which the line crosses the y-axis. For example, y equals 3x plus 2. The slope is 3, so for every 1 that x changes, y changes by 3. And the y-intercept is 2. Now let's graph y equals negative 2x plus 3 using the slope and y-intercept. Well, the y-intercept is found at 0, 3. And then negative 2x, oh hey, that tells us there's going to be another point at 1. Negative 2 plus 3 is 1. And then it's going to be 2, negative 1. And then we would plot the line through it. Now, given the slope and the y-intercept, graph each line. Y-intercept 2. Of course, we would plot that point 0, 2. And then for 4, we would find slope is 0.5. So half of 4 is 2. Plus the y-intercept. So y is equal to 0.5x plus 2. So for x equals 4, this would be 2 plus 2, so 4. 4. And then we could put a ruler through these 2 points and be done with it, if we so wished. Slope 1.5, y-intercept negative 1. Of course, we would plot 0, negative 1. And then slope 1.5. Well, 1.5 is easily multiplied by 1.5x minus 1. 1.5 is easily multiplied by 2. So we find 2, x equals 2 would give us y equals 3 minus 1. So 2, 2. And then we could just draw lines through these 2 points. Alright then, let's graph each equation using the slope and y-intercept. Y equals 3x minus 2. Well, that would begin at 0, negative 2, and, well, we could go for just 1, 1, and then draw a line through. Y equals 2/3 x plus 3. Well, we start with x equals 0 as usual, so 0 and then 3 and 2/3 x. That suggests we go for x equals 3 next. So 2/3 of that is 2 plus 3, that's 3, 5. All right then, next section. If you have the slope y-intercept form of y equals mx plus b, then if you know the slope and you know the y-intercept, you can substitute in. So let's write some equations. Slope is negative 1/4. Well, y equals mx plus b. Yeah, let's write that. It doesn't hurt. So then we substitute in negative 1/4 x plus negative 3, so minus 3. Here, slope equals 0. Y-intercept is negative 9. Well, y equals 0x, so we don't write that, plus b. So plus negative 9, that's just negative 9. Of course, y equals mx plus b does not hold if you're dealing with a vertical line. That's x equals some constant. Write an equation in slope-intercept form for the line passing through negative 4, 4, and 2, 7. Well, m is equal to y2 minus y1 over x2 minus x1. So rise over run. And it went from 4 to 7, so 7 minus 4. And it went from negative 4 to 2, so 2 minus negative 4 for the difference. So that's 3 over 6, because 2 minus negative 4 is 2 plus 4. So 6, so it's equal to 1/2. Okay, then let's find b. Y equals mx plus b. In this case, it's y1 equals mx1 plus b. y1 was 4 is equal to 1/2 of negative 4. You could also have done this with the other point, plus b. So that's negative 2 plus b is equal to 4. b is therefore equal to 6. So slope-intercept form, y equals 1/2. Oh yeah, we should probably put m over here. 1/2 x plus 6. You can feel free to check it with the other point that you didn't use when working out the y-intercept. Does it work? Oh, 1/2 of 2, that's 1, plus 6 equals 7. Wonderful. Write an equation in slope-intercept form for each of these lines. Slope equals 1, so y equals 1x, so just x. And y-intercept equals 2, so plus 2. Slope equals negative 3/4 x. Okay, fine. And y-intercept is negative 5, so plus negative 5. That's minus 5. Slope equals 0. Well, y equals 0x, so we don't write that. And then plus negative 3, so just negative 3. Write an equation in slope-intercept form for the line passing through each pair of points. So first, you find the slope, which is y2 minus y1 over x2 minus x1. So that's 1 minus 2 over 3 minus 6. Well, in this case, we ended up with negative 1 over negative 3. So 1/3. Now y1 is equal to mx1 plus b. So y1, well, let's use a 3, 1. So that's 1 is equal to 1/3 of 3 plus b. B is therefore equal to 1 minus, what's this? 1 equals 0. So, when you substitute these in, you get y equals 1/3 of, yeah, we should probably label that m, 1/3 of x plus 0. So we don't write that, just 1/3 of x. Now, 8, 8 and negative 4, 5. You have m equals y2 minus y1 over x2 minus x1. Now, we could go as 5 minus 8, or we could change the order, but changing the order is usually more trouble than just canceling some negatives, if applicable. So we're going with 5 minus 8 over negative 4 minus 8. So that's negative 3 over negative 12. So that's going to be, the negatives cancel, and that's 1/4. And now you have, y1 is equal to mx1 plus b. That's y1, let's use the 8. 8 is equal to 1/4 times 8 plus b. So that's 2 plus b is equal to 8. Therefore, b is equal to 6. And when we sub in, we get y is equal to mx, so 1/4 x plus b, so plus 6. Does this work for the other point that we didn't use just now? We can use this to check it. We can use this other point to check, and we get negative 1 plus 6. Oh, that's 5. Wonderful. Now, what about these 2 points? Well, you got m is equal to y2 minus y1 over x2 minus x1. So that's going to be negative 3 minus negative 3 over negative 5 minus 7. So it's equal to 0 over negative 12, which is equal to 0. The slope is 0. y1 is equal to, so mx1 plus b, and we substitute in. y1 is negative 3 is equal to m, which is 0, times x1, which is 7, plus b. So this just kind of goes away, so b is equal to negative 3. When we substitute all this together, we get y equals mx plus b. M is 0, so 0x just goes away. And then plus b, so plus negative 3 is just negative 3. You can use best fit lines, which are going to be linear functions, if you're plotting some scatter plots and fitting a best fit linear function to them. The usual use of the best fit line. The best fit line is very close to most of the data points, and you can use them to make predictions from real-world data. So you can make a scatter plot using some data, some numbers, and because these are coordinates, you can draw a line through them as best you can. Now, there is something very wrong with this. And that's because these data do not look like they would be a great linear relationship. In fact, you seem to have a two-stage linear relationship, where you go like that and you go like that. But you can make a scatter plot, and if you're asked to draw a best fit line for the whole thing, just do it. Use a best fit line to predict the percent of the population in the U.S. labor force in 2010. 2010 would be around here, which means that this would go up to a bit over 68%. Yeah, that makes very little sense. It's around we should probably mark out 2010. About 68.5%. Which is totally unreasonable. Which is unreasonable. As 2000 to 2003, 2000 to 2003 show a steady drop in labor force percentage. The data points should have a two-stage best fit instead. Because it seems to be going up, and then here it's going down. And if we go by the trend line downward, it would be somewhere in the neighborhood of 64%-ish around 2010. And we might put a bracket. Would give approx 64% in 2010. Alright, let's do some exercises. Here, this is a table that shows the number of girls who participated in high school athletics programs from 1973 to 1998. And also in 2003, apparently. We have an extra data point. Wonderful. Make a scatter plot and draw a best fit line. You plot all your data points, and then you put show trend line and make sure it's a linear fit, and it will draw your best fit line for you, which is very convenient. Now, the actual mathematical way to draw a best fit line is something that you get to discuss when it comes to linear regression in data management class in grade 12. So, if that, like AP statistics too. I'm counting AP statistics in there. So, can we use this to predict the number of female participants in 2008? Well, 2008 would be around here. And it seems like it's a pretty reasonable fit, unlike the example we had up there. So, going upward, we'd probably end up, well, that's the gap between 2,500 and 3,000, so we'd probably end up around 40% of a grid up, so approx 3,200,000 female participants expected in 2008. Of course, extrapolation is not as good in terms of its predictive ability as interpolation generally is. Extrapolation goes outside the domain of the data set you have. Interpolation is within the domain, such as, say you want to find how many girls participated in 2000 or 2001. Well, that wouldn't be so difficult. And it would also be reasonably accurate. Extrapolation, well, if you extrapolate too far, you tend to find some pretty ridiculous results. So, that's it for this chapter. We dealt with slope y-intercept form. And we noted that you can fit a line of best fit in linear form and get such an equation with which you can make predictions. Because plugging into a formula is easier than extending a line. Unfortunately, unless we use computer software, or a graphing calculator, we don't do linear regression until much later, which is why I only showed you guys that, hey guys, lines of best fit are linear functions. Now, if you use software, sure, you can actually find the line and plug in the numbers and make your estimates that way. But if you aren't doing that, well, as long as your scale diagram is well drawn, that works. It's worked for a very long time. It's the old way. Well, that's it for this chapter, so see you next chapter.